Thank you for the introduction. Good evening, everyone, and thank you for holding back till the last talk. So today I'll talk to you about one of the recent works from our group at UCSD, LocAP, an autonomous millimeter accurate system that maps Wi-Fi infrastructure. This work solves for one of the key missing components that enables wireless indoor navigation. Indoor navigation has many modern day applications, like going from one gate to the another in an airport during a transit that maybe some of you need to do in a while to go back. And even under mission critical cases where an EMT personnel is trying to reach their patient in a huge mall which they have never visited before. So we need indoor navigation to enable such important applications. Further, we all know that GPS does not work indoors. So how do we achieve indoor navigation? So the first thing we need to enable indoor navigation is to have a map to locate the user in, right? So there have been a lot of companies like Google, Apple, Bing, or Here's that provide indoor maps for many of the indoor spaces. Further, there has been a lot of research from the academia that provides user location indoors, amongst which a major of research is in Wi-Fi-based solutions because of its widespread deployment and its ability to penetrate many obstacles. There has been 2 decades of research in Wi-Fi-based indoor localization, while the first decade mainly focused on signal strength-based localization that only achieved up to a few meters of accuracy. In the recent past decade, there has been work that has achieved necessary tens of centimeter accurate indoor localization using channel state information. So you have mapping on one side and localization on the other side, right? So then why don't we have this navigation in our hands? Why can't we just pull out our phones maybe to navigate out of this conference room after the talk, right? You see, the problem is actually that both mapping and localization have been studied in isolation. What I mean by that is that indoor localization assumes that anchors in an abstract space and locates the user in this abstract space, and vice versa, where mappings services do not have the knowledge on how to provide user location within these maps. To be more precise, the core component missing is that we do not know the location of the Wi-Fi anchors in this given physical space. Say if we knew the Wi-Fi anchors in the physical map, then the last 2 decades of work can be made use to pinpointly locate the user within this given map. So with the work of LocAP, we open up this new research area wherein to enable seamless indoor navigation, one also needs to have accurate anchor location attributes. And we call this process of locating anchor attributes reverse localization, where we are the first work to even look into and establish the requirements on how accurately we need to reverse localize these Wi-Fi anchors. We find that these requirements are as stringent as requiring millimeter accurate mapping of anchor attributes. And so we develop a novel algorithm that reverse localizes these anchors accurately to millimeter level. To further automate this process of reverse localization, we deploy LocAP on this autonomous bot that you guys can see next to me, which goes around in a given space, mapping the space and also simultaneously reverse localizing the anchors. Finally, we demonstrate the performance of LocAP in a real-world environment and show that it meets these requirements, performing 50 times better than the state of the art. Before we dive into understanding and setting these requirements for reverse localization, let us see how state-of-the-art user localization algorithms work in estimating the user location. You see, the way these algorithms work is that an anchor measures the angle of the user with respect to itself in an abstract space, and when we measure the angle from multiple anchors, we can simply triangulate the user and estimate his accurate location. This makes the knowledge of exact anchor location and its orientation within a given physical map very important. Further, these algorithms estimate the user direction by measuring the additional phase of the signal traveled at the next antenna with respect to the first antenna. And this additional phase is proportional to both user direction, which helps in estimating the user direction. Also, it depends on the antenna separation. And a natural consequence is that it makes the knowledge of exact antenna separation very important. So now, what happens when there are errors in these anchor attributes? By anchor attributes, I mean both the anchor location, its orientation, and also the antenna separation. You see, any error in knowing the exact anchor location would directly reflect to similar error in the predicted user location. Further, any error in knowing the exact anchor orientation causes a rotational error at the user as well. And finally, we have seen that antenna spacing plays a key role in estimating the user direction. So any error in antenna spacing, antenna separation, also causes a rotational error at the user location. And this is the reason we need to exactly know the anchor attributes, which includes knowing exact anchor location, anchor orientation, and antenna spacing on the anchor. To further quantify these requirements, we have set up an 8 meter by 10 meter simulated environment with 3 anchors that are triangulated in the user location while the user moves to 100 different locations. Using this setup, we analyze the tolerable error on each of the anchor attributes independently. For example, we have seen that not knowing the exact anchor orientations causes rotational error for the user location predicted. So we report incrementally erroneous orientations of anchors to the user localization algorithm and observe the following plot, where on the x-axis is orientation error in degrees, and on y-axis is a median user localization error reported by the algorithm for a given orientation error. To quantify the requirements, we set a hard target of achieving 50 centimeter median localization error for decimeter accurate indoor localization. And we find that to achieve this 50 centimeter median user localization error, we need anchor orientation predicted accurate to less than 7 degrees error. Similarly, we have analyzed each anchor location attribute individually, and we found out that for achieving decimeter level user localization, in addition to knowing the deployment orientation to less than 7 degrees error, we would need to locate the anchor point location accurately to less than 25 centimeters median error. And finally, we realized that we need to predict the antenna separation on the anchor accurately to less than 5 millimeters. And these stringent requirements make it impossible to manually label or measure these anchor locations, anchor attributes. And this is mainly because manual labeling or measurements of these millimeter accurate antenna separations or less than 7 degree orientation predictions is very tedious and would require expert civil engineer measurements. So in order to avoid manual measurements, we make the reverse localization of anchors autonomous by deploying LocAP on this autonomous bot next to me that is equipped with visual SLAM algorithms, which gives us accurate location of itself. We mount a Wi-Fi client on top of the bot that collects channel information for each bot's location and uses this channel information to reverse localize the anchors. While this bot goes around and maps the spaces, it also uses LocAP that's running on the server on it to accurately map the Wi-Fi anchors within the physical map. Now that we have seen how LocAP is deployed, let us dive in and understand how LocAP achieves accurate reverse localization of anchors. Firstly, let us see how LocAP predicts the anchor location accurate to few centimeters. The first question that comes is, what should we define as the anchor location? So in LocAP, we locate one of the antennas on the anchor and call it the anchor location. We also call this the first antenna. Now that we have defined the anchor location, how do we locate it? Since we know the exact bot location, we can make it a vantage point and measure the direction of the anchor by utilizing the existing user localization algorithms applied in reverse. And since we have the bot going around, we have hundreds of bot locations using which we can accurately locate the first antenna. Unfortunately, the errors in bot location estimates can be more than tolerable. So we propose a novel visual sensor-based confidence metric, which basically says that the lower the confidence for a given location, the higher the error in bot's location estimate. And using this, we neglect for bot locations that have low confidence metrics and achieve centimeter accurate anchor locations. So now that we have achieved the centimeter accurate anchor locations using hundreds of bot locations, a natural question would be, then why not just extend it to locate all the antennas and get millimeter accurate measurements? Unfortunately, we found out that this form of combination quickly saturates to 3 centimeters even with just 20 bot locations. So we cannot meet these stringent millimeter accurate requirements for antenna separations. Then how do we bridge this gap in performance that we have? Before answering that, let us try and understand why this accuracy saturates. The existing Wi-Fi infrastructures have a maximum bandwidth of only 160 megahertz, which could resolve up to only 2 meters in distance. And after combining across multiple bot locations, maybe we can bring it down to a few centimeters, but like we have observed, not any further. On the contrary, the first key insight of LocAP is that the carrier frequency for the Wi-Fi is about 5 gigahertz that can provide millimeter accurate distant measurements. What I mean by that is, it is quite easy is that when we consider one single wave, which is of 6 centimeters for 5 gigahertz carrier frequency, and that corresponds to 360 degrees phase, it's easy for nowadays for any receiver to measure phase of approximately 6 degrees in difference, which gives us up to 1 millimeter accurate resolution. So now let's understand how this phase difference at carrier frequency can be utilized. So any signal that is arriving at an antenna array, for each additional antenna, the signal travels an additional distance of d sine theta, where theta is the orientation in which the signal is arriving, and d is the antenna separation that you want to measure. And this phase difference measurement is done at carrier frequency, thereby giving us the advantage of its high resolution. So the intuition of LocAP is that instead of locating each antenna independently, we will locate all the antennas of the anchor with respect to the one antenna, thus achieving relative phase difference advantage provided by the carrier frequency. Let's formally look at the solution, and for simplicity, let's just consider a 2 antenna case where you know one of the antenna's location from a previous anchor location algorithm. We will now locate the second antenna relative location with respect to the first antenna, thus enabling joint estimation of both antenna separation and orientation, d and psi, respectively. As we have discussed, LocAP's first intuition is to measure the phase difference across these 2 antennas. But this phase difference has 2 unknown quantities. One is antenna separation d, and the direction in which the signal has arrived, theta 1, because we don't even know the orientation of the antenna anchor. And we see for a given bot location, we know beta 1 that we have estimated earlier, because we know both the bot's location and also the anchor's location. And so we see that theta 1 is related to psi as described, as shown. So what we have is one phase measurement with 2 unknowns, antenna separation d and orientation psi, which is also dependent on theta 1. So how can we overcome this limitation? Since LocAP is deployed on an autonomous bot, we can use multiple bot locations where for a given antenna separation, we see there is a unique rate of change of orientation, theta 1, that can be plotted for multiple points, and thus we can estimate both d and psi simultaneously. Unfortunately, when the actual antenna separation is lambda, we can see that the same phase values has ambiguous solutions, which limits us from joint estimation of antenna separation and orientation. So instead of using phase difference across multiple bot locations, we use the differential phase across these multiple bot locations, and by which I mean that we estimate the rate of change of phase with respect to the bot's location, and use this differential phase difference to accurately reverse localize the anchor attributes. So in LocAP, we observe that though phase difference has ambiguity, the differential phase difference with respect to the bot's position is unique for all antenna separations. And using this, we achieve millimeter accurate antenna separation and less than 7 degree accurate orientation prediction for LocAP. Further details on exact formulation of how we use differential phase difference to get these measurements is further described in our paper. Further, we also have assumed so far that we have the phase corresponding to the direct path, and our novel multipath algorithm is further detailed in our paper. Due to limited time, I ask you to take a look at our paper for further information on this end. But now let's see how LocAP is deployed and how does it perform in real world settings. To evaluate LocAP, we have tested it on 8 different commercial off-the-shelf Quantenna boards, spaced around in a 2,000 square feet space. Among these 8 anchors, we have 5 different antenna separations ranging from 0.5 lambda to 2.5 lambda and 7 different anchor orientations. We also had used the most popular antenna geometries out there, linear and rectangular antenna arrays. Further, since all the processing is done on the bot's end, which has a Wi-Fi client, we do not need any changes to be made to the anchors we are locating. With this setup, we demonstrate that LocAP achieves accurate reverse localization and compare it against SpotFi, the state-of-the-art Wi-Fi localization algorithm. We see that for predicting anchor antenna separation, where the requirement we set was about to achieve 5 millimeter median error, while SpotFi achieves 150 millimeter median error, LocAP achieves 3 millimeter median error, showing a staggering 50 times improvement in antenna separation prediction. Further, we presented a requirement of less than 7-degree median error for anchor orientation prediction. And while spot-fi median error is about 25 degrees, LocAP achieves 3-degree median error, showing an 8 times better performance, thus showing that LocAP meets both stringent millimeter accurate requirements we have set earlier. There are further results and micro benchmarks and case studies that we present in our paper. Please go back and take a look. In conclusion, LocAP is the first work to identify this new field of reverse localization of anchors and defines requirements for reverse localizing these anchors as well. We also developed an algorithm that locates these anchors' location attributes accurate to millimeters in real-world deployments. Thus, locating these anchors accurately, we enable indoor navigation, which can further be used for applications like VR or even in communications, wherein we are going more towards these directed beams that require user location. Thus, unlike the current communication systems that drives the user locations, we are moving towards where exact user locations are needed to be able to effectively communicate. You can also find further details of our work on the following website, where we are also planning to release the largest Wi-Fi indoor localization dataset out there that enable our other deep learning-based user localization work published in Mobicom 2020, where we hope you'll be able to join us again. Thank you, and I'm open for questions.
Hi, Arun from MIT. Hi. This is very relevant work to make localization practical. Thanks. So how much work would it take to make it to go from a bot to something I can carry around, so to remove even the cost of the bot itself?
Yeah, so like I've said, the bot uses its visual sensors to get the location estimates, and we are getting there where phones have this time-of-flight cameras, and once we have these enabled, and where phones can provide you accurate movements across time, you should be able to.
So the inertial sensors and the bot are not important?
Not actually. The visual sensors are more important than.
Arun from CMU, one last question, please. I was wondering, so you're using SLAM for localizing the robot itself, and the robot is pretty much moving in every single room. So did you think about, okay, why not use image recognition, use a camera-based approach to track where the access points are and where the antennas are? So where did that fail?
Yeah, so I think all the antennas are not visible for most of the anchor points. Then they try to hide them for some reason, and even then, even if you can find one, even in this room, you cannot actually locate the anchor points just with using visual sensors. And Wi-Fi in that way, it is more pervasive.
Thanks. I have one question.
Yeah.
So how sensitive is this approach to the localization of the bots itself?
So for anchor location in itself, it is sensitive up to 6 centimeters. We have presented the micro benchmarks in the paper as well. And for anchor orientation and relative anchor prediction, it is sensitive only up to 0.1 millimeter for user.
Awesome. Thank you. Let's thank the speaker one more time.